Now, when I spoke to you the very first day, I said that this module was all about AWS, and that starts today, really. So I've got two new cards on the website. We'll get through both of them, but there's going to be a lot more on the second card that I will add on the next lecture. So I won't cover all of the serverless stuff today by any means. Each of these has a lab associated with them, as usual, but these labs now you do not have to submit, but obviously they're important because they build up to ultimately the first assignment. So behind this card here, there's a set of slides and a lab, as I said. So we'll work our way through this set of slides. Should be reasonably quick to get through them, I think. And really, what we want to achieve in this module is the ability to develop applications that run in the cloud, as it's put, and specifically in the AWS cloud environment. And that involves not only writing code, the code or the functionality of the application, but it also concerns provisioning infrastructure, as it's termed. Infrastructure is a combination of compute infrastructure, like where our code actually runs, the platform that it runs on. It would also include, let's say, some file storage infrastructure, possibly. We may want to upload files, be that images or whatever, as part of our application's functionality. It certainly may involve a database. So all of these parts of our application require infrastructure, and that infrastructure needs to be created or provisioned. And the question is, how do we provision or create that infrastructure? And one solution in the context of the AWS platform is to use the Cloud Development Kit as a way of provisioning the infrastructure that we require. Now, the AWS CDK or Cloud Development Kit, it's been around not that long. 2019, I think, was when it came out first. But there are two versions of it, and we certainly want to use version 2. So if you're reading any articles that relates to version 1, which is unlikely because they would be about 5+ years old, then you're probably better off not reading it and try and find stuff related to version 2. But pretty much any Google search that you will do on the CDK will relate to version 2 more than likely. So the context, as I said, is we want a way of provisioning infrastructure for our application. And whatever way we go about doing that, we'd like to be able to do it in a way that is reliable and consistent. And the reason for that, apart from the obvious, but the reasons for that are we may need to provision the infrastructure multiple times. Because, for example, we may want to provision the infrastructure across multiple environments. We may want to have a development environment, a test environment, a production environment. And each of these environments, we will create the infrastructure on each of them. And so we're going to be creating the same infrastructure multiple times. Also, where it may be an issue is if you want to run your application globally, then in relation to AWS anyway, as you may or may not know, the AWS cloud is broken up into multiple regions globally. I just checked there a moment ago. There are 33 regions the AWS cloud comprises of 33 regions. And so if you want to run your application on multiple regions, not necessarily all 33, but if you do want to run it in multiple regions, then that means you need to create the infrastructure in each of these regions. So for both of these reasons, the way we go about provisioning our infrastructure, by provisioning again, I mean creating the infrastructure and configuring it. The way we go about that needs to be in a consistent way, so that if we do need to repeat it multiple times, and I've explained why we might need to, then we want to make sure that we create the exact same infrastructure each time. Now, certainly, if you want to do something multiple times and you want consistency, then a manual approach to that is not desirable for obvious reasons, because humans don't tend to be consistent in the way they do things. So it lacks consistency. Secondly, a manual approach, I'm saying here, lacks a single source of truth. This is an expression that we use a lot in software engineering. You know, the steps that you may need to go through to provision the infrastructure, okay, you may document them and make that document available to other people that may need to provision the exact same infrastructure. And that's fine, but over time, that document is going to get out of date because presumably the infrastructure may change over time, or the infrastructure requirements may change over time. So any kind of manual documentation, while it might be great initially, it eventually becomes out of date. And you know, there are multiple copies of the document floating around the place. And so that all adds to inconsistency in the way the infrastructure may be recreated over time. And so for these three reasons, we don't like a manual approach. We'd like to automate it because we know automation is something that can be repeated and it does the exact same thing every time. So we actually want a way of creating the infrastructure or provisioning the infrastructure in an automated way. And that really means coding it in somehow. So we actually want to be able to create our infrastructure using code, hence the expression infrastructure as code. And that's what the CDK is all about. So this term infrastructure as code, it allows organizations to automate the provisioning and configuration of cloud resources there. So resources is our infrastructure in a consistent way. And just because I'm aware, I'm conscious of the fact now that some of you have no experience of AWS. So there's a lot of terminology around every technical topic, and it's no different for this subject. So when we talk about resources, so the AWS cloud is comprised of many services, and we use a service to create a resource. So for example, examples of resources might be, we might want to create an EC2 instance for ourselves. An EC2 is essentially it's a virtual machine. So that's a resource that we might want to create as part of our infrastructure. Or in relation to file storage and object storage, there's an AWS service called the S3 service, simple storage service. So we may, and it talks about buckets. So a bucket is essentially equivalent to a folder. So we may want to create an S3 bucket as part of our infrastructure. That's another example of a resource. In the database world, AWS has multiple database services. One of them is called DynamoDB, which is one that we will use. So we may want to create a DynamoDB table resource as part of our infrastructure, and so on. So SQS is a messaging resource. I'm not sure if you have any experience of messaging, but we will try and include it as part of this module. You can also create your own your own virtual network on the AWS platform. We call these networks virtual private clouds, or VPCs for short. We won't do very little on the VPC side of things, but certainly S3, DynamoDB, SQS will all be part of what we'll be concerned with creating. So IAC, infrastructure as code, it allows us to express the infrastructure that we want for our application, express it as code, and then on the execution of that code, the various resources are created by the AWS platform for us. And so because we're implementing it as code, then we get the benefit of version control over that code, and we know what the many benefits of using a version control tool on code is. We can roll it back, see what changes have been made, who made the changes, etc., etc. So so a version controlled repository that really becomes our what do we call it on the previous screen? Our single source of truth. So the repository, GitHub, let's say repository, becomes our central source of truth for how we create the infrastructure for a particular application. And we can roll back changes, that's as a consequence of also, we can share best practice across multiple projects by not documenting, sorry, but by having repositories that contain good quality infrastructure as code, or best practice infrastructure as code. So this idea of infrastructure as code has been around for a while, and it has evolved. Now, originally, the way we achieved infrastructure as code, I'm trying to get across on this screenshot here. So on the right, we have the various, on the right, we have the various, some services that are provided by, let's say, the AWS platform. And what we could do in the early days is we could write a script, typically in Python. So this is my script here. And that script could send requests to our services, asking them to create a particular resource. So we might send a request to the S3 service to create an S3 bucket for us, or send a request to the EC2 service to create a virtual machine instance for us. So that was kind of the first approach that we had towards implementing the automation of infrastructure provisioning by writing an actual script. But the problem with that, and there were many problems, I'm documenting down here. So this script, when you run the script and you run it on your local desktop, it's sending requests across a network to the various services and getting them to create the particular resources that we want. But I'm saying what happens if an API call fails? Okay, by an API call, I mean one of the requests made from our script to one of these services. So what if, I've got a number of requests being sent from my script here, and the first request works, the second request works, but the third request to whatever service, let's say that fails. I'm kind of in a middle ground now, because that means some of my resources have been created, but some of them haven't. And I really now have to go manually checking to see which resources have been created, and maybe delete them again and run my script all over again. So, it was very clumsy in that sense. Otherwise, you'd have to build into your script, you'd have to build in some exception handling to deal with various scenarios, but there could be multiple scenarios. Also, let's supposing I ran my script and it ran perfectly, and all of my resources were created, all of my infrastructure was created on the AWS cloud. But let's supposing I want to make some changes I want to add some new resources, change the configuration of existing resources. that means I really have to write a completely new script where the starting point for this new script is the current infrastructure that has been created. So there's no, like, I can't really go back to the original script and make edits to that. It's really a completely new script that I need. And that's not great, really. Number three, how do I know when a resource is ready? Because, we're making network calls across here, and the creation of a resource by a particular AWS service, that's going to take time. So how do we know, let's say if later on in our script, we need to use a particular resource that we wanted to create earlier on in the script. How do we know whether it has actually been, whether the creation has been completed or not? Again, we could build it into the script, but our script is getting bigger and bigger now at this stage, really, and it's getting more complex. And also, how do I roll back? That kind of relates to the first point. So it was okay. It was automation, and it was fine if the infrastructure that we wanted to create never changed. So, once we got our script correct, then we could run it multiple times and it would create the exact same infrastructure each time. That's great, but it certainly doesn't deal with changes to your infrastructure if you want to implement updates to your infrastructure. Then the cloud providers, and we're only interested in AWS, but they all do the same thing. The cloud providers provided what's referred to as a resource provisioning engine, which is essentially just another service, but this service is specifically aimed at creating other infrastructure for you. And so the way these resource provisioning engines worked, and in the case of AWS, the resource provisioning engine is a service called CloudFormation, which I'm documenting here, right? So what you had to do is you had to describe the infrastructure that you required, typically using JSON or maybe YAML. You could use either one. In the case of AWS anyway, you described your infrastructure using JSON or YAML, which is code, okay? But it is declarative code. So you wrote what's called a CloudFormation template, and then you uploaded that template to the CloudFormation service, and it interpreted that template, and it went off and it took care of communicating with the other services to create the infrastructure for you. And it took care of all of the problems that we documented on the previous slide. So it took did a lot of the heavy lifting for us. So as a developer, you wrote your CloudFormation template, you uploaded that to the CloudFormation service, and it took care of making all the API calls to the various other services to create the resources that were required. So the advantages it had was it was actually quite easy to update your infrastructure. To update your infrastructure, you just went to your template and you made the necessary changes, because the template now is just a declarative statement. Let's say it's just written in JSON. So you made the relevant changes to the parts of the JSON, reflecting the changing configuration that you wanted to make to particular resources, or if you wanted to add new resources, you just added the relevant JSON. If you wanted to delete certain resources, you just deleted the particular parts of the JSON. So you edited this in the normal way. Then you gave the edited version of the template to CloudFormation, and it took care of working out what changes need to be made to the resources. And it sent the relevant requests then to the other services to carry out those changes. Again, it did all that heavy lifting for you. So it was able to work out the difference between the first version of the template that you gave it and now the updated version of the template. It took care of working out the differences between the two of them and making the appropriate requests then to the other services to carry out the changes that were required. So that was a major improvement in the whole infrastructure as code evolution. Disadvantages with this approach, though, was that you wrote your uh, you wrote your code in the form of JSON or YAML, which isn't the nicest form of coding available to us. Also, um, the actual template files were very long, so hence they were kind of error prone. Because there was no way of there were no abstractions available to you in this templating world. Everything had to be specified. Every particular configuration setting for whichever resources you required, you had to be specific about each one of them. There were no default values, or there were no high level abstractions that you could use, which is typical in programming. All of programming involves using abstractions, but we didn't really have that in this resource provisioning engine kind of world. Just taking a step back, so I haven't introduced CDK yet. This is another way of looking at how things have evolved over time. So at the very beginning, so AWS dates back to around 2006-ish. And back then, the only way we could create resources is through the web interface, which, in other words, uh, here, right? We had to manually go into each service. So if I wanted to create an EC2 instance, I went into the EC2 service, and I followed whatever I wanted to go to instances, and I start here. I've never actually launched an instance there on the top right, and it steps you through various steps that you have to go through to create an instance, the configuration for it, etc., etc. So, that would essentially be a manual approach. That was the way you did it on day one. But what AWS did was they put a web API front end to all of the services that it had back then. And because there were these web API services, that allowed us to write our scripts that I was talking about a couple of slides back, where our scripts were now communicating with the web APIs, sending raw HTTP requests across. But at least we could write code now to create infrastructure rather than doing it manually via the web front end. This is also, by the way, we also refer to this as the management console, the AWS management console. So in my diagram on the right there, I'm showing you that, first of all, we got these web APIs available to us, and that allowed us to do our scripting. The second thing that happened was the AWS actually provided SDKs. I'm losing my mouse, sorry. Provided SDKs, software development kits, and they took care of making the HTTP calls to the web APIs. So now our scripts that we wrote were using SDKs rather than making raw HTTP requests. So if you've done any Python scripting with AWS, you may have heard of the Boto 3 SDK, but every language, JavaScript, Java, Python, Go, C#, the AWS people, they released SDKs for each of the languages. So we could write our scripts in any language that we wanted to. Then the resource provisioning engines came into existence, and I'm saying that was around 2011. So the AWS network dates back to around 2006. So about 5 or 6 years later, this resource provisioning facility became available to us. Now, the major, as well as these resource provisioning engines having all of the advantages that I mentioned on the previous slide, critically, what they did is they managed what I'm calling state here. And by state management, we mean the state of your infrastructure. In other words, what are the various parts of your infrastructure and what is the configuration settings on each part of your infrastructure. And if you wanted to change your infrastructure, i.e. change the state of your infrastructure, all you had to do was, as I was trying to explain on the previous slide, was all you had to do was update the template and then give that updated template to the CloudFormation service, and it took care of changing the state of the various resources via the other services that were managing those resources. So so CloudFormation came in around 2011. The rest, the web APIs, not sure when they became available, but it predates CloudFormation, obviously. That's fine. I'm mentioning this thing called Terraform down here, and it's also mentioned up here, right? Terraform is an open source variation on this CloudFormation templating. We won't be using it, but it's also Terraform works with all of the other cloud providers, whereas CloudFormation templates are specific to AWS. These Terraform templates as well could be used with other cloud providers. Now, eventually enter the CDK. And what the CDK gave us was it actually allowed us to write our infrastructure as using imperative programming languages. Whereas with CloudFormation, we use a declarative language for describing our infrastructure, i.e. JSON or YAML. But with the CDK, we could describe our infrastructure using an imperative programming language. And there are multiple languages that we can use with the CDK framework. We will be using TypeScript, but you can use Python, Go, Java, and many others. And we're very familiar as developers, we're very familiar with imperative programming languages. We're less familiar with declarative programming languages. Also, what imperative programming languages give us is the ability to have various abstractions, which means we write less code. So I'm saying around August 2019 was the first release of the CDK framework. Its goal was to describe infrastructure in an imperative language. And as I said, there are many languages that it supports. Also, the CDK provides quite a large class library, and we will be using a small subset of the classes, and it's these class libraries that come with the framework. That's what they will contain all of the abstractions that make our implementation much easier than in the case of using CloudFormation templates. And so the whole developer experience is arguably much better using this imperative approach versus the declarative approach. As in we write far less code. LOC here stands for lines of code. So the number of lines of code that you had to write in the CloudFormation templates, CF there stands for CloudFormation. The number of lines of code that you had to write was far, far greater than the number of lines of code that you write using the CDK framework. And I'll give you an example of that in a moment. Also, the IDEs that we use, you know, they have hinting and intelligence built into them, which we were very familiar with from programming in general, whereas you didn't really get that kind of assistance when you were writing your CloudFormation templates. You could do something like unit testing as well, but we won't be going near that. So enter the CDK. And so in the world of CDK, we develop what we call CDK applications or CDK apps. And an app is comprised of stacks. A stack is comprised of constructs, and a construct is comprised of many resources. So resources are ultimately the things that exist in the cloud itself. But due to the benefits of using an imperative programming language, we have abstractions that we can use. And so constructs is the main abstraction that's available to us. And an abstraction is a construct is contained within a stack, and a stack is contained within an app. So visually here, you kind of get a visual representation of what a CDK application looks like. Now, in our case, our CDK applications will just consist of one stack, but there'll be a number of constructs within each stack. And a construct then, when it's broken down, will create the instructions required to create individual resources. The unit of deployment is a stack. So we can imagine now, here's what we develop within our IDE, and ultimately what actually happens is the code that we write in an imperative language, that is actually converted into the CloudFormation templates that I've been talking about, because we always have to go back to CloudFormation in the case of AWS. But the translation of our imperative code into CloudFormation declarative code, that is taken care of for us by the CDK framework itself. And we know what happens after that. And once CloudFormation has its CloudFormation template, then it takes care of communicating with the various services to create the resources. A very simple example, if I want to create an EC2 instance, which is essentially a virtual machine instance, if I want to do that using the CDK framework, roughly anyway, I have to write, it looks like 12 lines of code. And that 12 lines of code is converted into CloudFormation syntax. It turns out it builds up to 150 lines of code. So straight away, you get a sense there of the benefit of implementing infrastructure code using an imperative language rather than a declarative language. This is the kind of flow of execution when you're using this CDK framework. So we as developers here, we write our imperative code, which is describing the infrastructure that we require. So our infrastructure as code is implemented in imperative language. That code then is taken by the CDK framework, and it creates a declarative CloudFormation template equivalent. That template then is given to the CloudFormation service, and it takes care of communicating with the various services like EC2, S3, etc., etc. It communicates with those services, and the services then create individual resources in the cloud for us. And a collection of resources is contained within a stack. So these resources have to be related to a stack. And way back here, we would have created a stack construct as well. The workflow is typically like this. Okay, you do a CDK init, you create a boilerplate CDK app. You do have to specify what language you want to implement the infrastructure as code in. And as I've already said, there are many languages, but we will be using TypeScript. Coincidentally, the CDK framework is implemented in TypeScript as well, but that's just a coincidence. So this command will do the scaffolding for you of your CDK project, if you like. Then you write your infrastructure code, and this command is optional. What the sint command does is it creates a local copy of the CloudFormation template. We don't ever really need to look at those templates. You can glance at them yourselves, but it can be quite difficult to read. This is the main command. When you do the CDK deploy command, that is what kind of triggers sending the CloudFormation template up to the CloudFormation service, and it goes away and does all of this stuff here that I was describing. After you've done your CDK deploy, you now have the, if you like, the initial version of your infrastructure, and you can go back to your source code and make changes. And if you do make changes, all you've got to do is run CDK deploy again, and this time the command will compute a new CloudFormation template, send that new updated CloudFormation template up to the CloudFormation service, and it takes care of doing a diff operation between the current state of your infrastructure and the new state that you want it to move into, and carries out the necessary instructions to the various services to make the necessary changes to the state of your infrastructure. Eventually, but you can do this at any stage. If you run the CDK destroy command, what that will do is destroy all of the infrastructure. And that's something that we will do an awful lot. Create infrastructure, play around with it, destroy it, as we'll see. So when you do the CDK init command, it creates a boilerplate project for you, and this is what it looks like on the right. And really, there's only one file you spend most of your time editing, which is this one here. But just to go through it, so there is a file, because we're using TypeScript, they have TypeScript file extensions. So this file here is what I'm saying on the right. I'm saying it's on the left. It's the entry point for the CDK framework. And within this bin file is where you essentially, you instantiate your app, and you specify the stacks that are part of that app. In our case, there will only be one. So there's very little code in this file in the bin folder, but it is the entry point for the framework itself. In the lib folder then is where you have, typically, you have one file per stack. And within that stack file is where you describe, using the imperative language of choice, in our case TypeScript, the various resources that you need, although you don't specify them at the resource level, you specify them at the construct level. And that's okay. And then there is a testing, you can see there are testing folders down here as well, here, but we won't be going near that. We just won't have time. So in terms of the code that we write inside in our stack file, we create constructs, and a construct now is it's a CDK concept, right? And there are three types of constructs. We will pretty much be creating L2 constructs all of the time. And these constructs are just abstractions, which is one of the benefits of using an imperative programming language. But there are L1 constructs, L2 constructs, and L3 constructs. L2 constructs, when you create one of them, and they're just they're classes really, and when you create an instance of them, you're creating an instance of the construct. But behind the scenes, creating an instance of that construct will translate into creating a number of AWS resources up in the cloud. So there's a one-to-many relationship between an L2 construct and an AWS resource, which is kind of one of the benefits of this whole imperative approach. So there's a one-to-many relationship with a CF. CF always stands for CloudFormation in my slides, with a CF resource. And the benefit of these L2 constructs is that you don't have to write as much code as you would have in the templating world, because there's lots of default values that the construct will apply to various configuration settings. You can overwrite them or override them, obviously. But if you were happy with the defaults, then that means you have to write far less code. The L1 constructs, there's a one-to-one relationship between an L1 construct and a CloudFormation template resource. Okay. There's only one case where we have to use an L1 construct. L3 constructs then are kind of higher level again. We won't be using any of those. So here's a CloudFormation project that I created earlier on, and it has the exact same structure that I was talking about there on the slides. And so here in this file here is where we write our infrastructure code. I suppose if we look at this one first. And even before that, maybe we should just glance at the package.json. So it is because we're using TypeScript, this is a node project. So you run your CDK, you run npm install at the very beginning, and the dependencies are fairly predictable. You know, here's the actual CDK class library that I was talking about. This is another part of the class library. We needn't worry about that one. So they're all fairly predictable. And dev dependencies, these are just TypeScript declaration files, you know, these .d.ts files that we're bringing in. And there's some other TypeScript stuff in there as well. So anyway, you run npm install on that. So here's the actual CDK app entry point. And what are we doing? We're just creating an empty CDK app. Then we're creating a stack. This class, you can see we're actually importing it. So, which we'll look at in a minute. Where are we importing it? There, we're importing it here. So this is my stack, and I'm essentially attaching my stack to the app that I created on the previous line. And that's it, really. I'm just giving a name to the stack. It can be anything you want it to be. And we don't tend to need, but I am specifying here the region that I want this stack to be deployed to, because you do have to specify a region for the stack. But I think if I even left that out, it would pick up the region based on the configuration of my AWS CLI. And this is my AWS account number. But I think I could actually have left that out, and it would pick up my account number so that it deploys the stack to my account. And that's all that's in this file. So very little. That's where. So in the file, you create your CDK app and you attach your stacks to that app. And so if I had other stacks, I would have a line similar to this line. So that this stack brings me to, this stack here is implemented in here. And apart from the imports, a stack, it looks like, is a class, TypeScript class, call it whatever you want to, and it extends the stack class provided by the CDK framework itself. And it's really only the constructor that we implement in this class. You can see here my constructor begins here, and there's nothing else other than the constructor. So you don't tend to have lots of methods for this stack implementation. And in my stack, the only thing I wanted to do is I want to create an EC2 instance. And so here's the code to create an EC2 instance. And in terms of my construct, in terms of creating an EC2 instance, this here is an example of an L2 construct. So not only behind the scenes, not only is it going to create an EC2 instance for me, but it's going to create some other resources as well, like security groups, an IAM role. You may not be familiar with these terms now, but it does create a number of resources as well as the EC2 instance. But we needn't worry too much about those other resources. That's the whole point of using this imperative approach. And so I'm creating an EC2 instance for myself. I have to attach that instance to a stack, and that's what I'm referring to. This here refers to the enclosing or encapsulating stack, if you like. I can give a name to my resource, and that's all I'm doing with that string. And this part here then is the configuration settings that I want. Yikes. The configuration settings that I want for my EC2 instance. But there are many other settings that I'm not specifying. And in fact, probably some of these I didn't need to specify as well. But there are a whole set of other settings that I'm not specifying, which means I'm taking whatever default values are being assigned to them by the particular L2 construct that I'm using here. So that's an example of the fact that I have to write far less code because there are default values being assigned for me by the construct. And, you know, the detail isn't that important, but essentially I want it to create an EC2 instance, and I want it to load the a Linux operating. I wanted to load a particular version of the Linux operating system onto that EC2 instance for me. Some of the other settings I wouldn't worry too much about. This line here that I've kind of skipped over, when you create an AWS account, then the AWS platform creates a private network for you on that account. That private network is referred to as a VPC, or virtual private cloud. So everybody, once you create an AWS account, you have one VPC assigned to you. You can create other ones. I didn't in this case. I just said, look, find the VPC that's associated with my account, and I want my EC2 instance to be launched inside in that VPC, inside in that network, if you like. So, and that's all I have in my stack. There's some other stuff that I'll bring in a moment. So that's my stack implementation. And so from the command line, I've got to run the command cdk deploy. Just bear with me for a second. CDK deploy, you can see there at the bottom. Now, I did it just before the lecture because it can take a little bit of time. But if I hit return, then what happens behind the scenes is, as I said, the CDK framework is going to take my imperative implementation. It's going to create a CloudFormation template. In fact, it puts the CloudFormation template into the CDK out command folder. So if we drill down in there, we would find that's it there, I think. Let's see. It should be longer than that, I think. Oh, there it is here. Okay. There's my CloudFormation template. Okay. So that's the equivalent, and that's what it sends up to the CloudFormation service. And the CloudFormation service executes, if you like, the template. And eventually what it did was, if I go to the management console and I go into the EC2 service, am I there already? I am, yeah. I go into the EC2 service, and if I select the instances here on the left, you can see here is the EC2 instance that it has created for me. And if I just select that, get some information on it, here's the IP address of that EC2 instance. Now, at the moment, that EC2 instance, that virtual machine running the Linux operating system, is up and running in the cloud, but I cannot access it at the moment. The default is such that I cannot connect to it using, let's say SSH. That's the default setting. So I want to try and SSH to my EC2 instance. In order to do that, I've got to add some infrastructure to my stack. So if I go back to here, and here's the extra little bit of code that I want to add. Now, again, I'm kind of conscious of the fact that some of you have done some AWS and some of you have not, but I do need to move this code up before my instance. Now, the code that I've highlighted here, what it's doing essentially is it's creating a firewall rule, and the firewall rule is saying, let's see, the technical term is we're creating what's called a security group, an EC2 security group, which is a bit like a firewall. And I want to attach this security group stroke firewall to my default VPC. And I want to make all outbound traffic, all ports, essentially outbound ports, enabled for this firewall. I'm adding another bit of configuration to my firewall. An ingress rule is an inbound traffic, and specifically, I'm saying I want to open up port 22 for inbound traffic to this firewall, and port 22, as you know, is the SSH port. So I'm enabling port 22 on my firewall, but I now need to link this firewall with my EC2 instance, and that's a configuration setting. And so if I add, and here's the benefit of using TypeScript, because TypeScript is telling me possibly what I want to type in here. And in my case, it's security group. So I'm attaching the security group that I've defined just above, or the firewall, and I call this server SG. Now, before I, sorry, now, so I'll save that. So again, I've just created a security group stroke firewall. I've added some rules to this firewall, and I've attached the security group to my EC2 instance, which means that it applies to it. Before I do a CDK, so I've made changes, sorry. And to have these changes applied, I just run the CDK deploy command again. But just before I do that, if I go back to the management console, and if I look at the current kind of configuration of my EC2 instance, so here I'm looking at, if I select the security tab here, and you can see there is a security group currently linked to, there is a security group currently associated with my EC2 instance, but the security group is the default security group that's given to any new EC2 instance. And if I select that, and what this is showing me now is the configuration of this particular security group. And the two things that I'm interested in are inbound rules and outbound rules. In terms of inbound rules, in other words, what ports are open for this security group, then you can see that there aren't any. In terms of outbound rules, it seems to have one rule that is essentially saying all outbound traffic on any TCP port is allowed. But there are no inbound rules at the moment. That should change now, though, once I do a CDK deploy here. So when I hit return here now, the CDK framework is creating a new version of my CloudFormation template. It's asking me, am I okay that I'm opening up some security issues? That's okay. Creating a new template, sending that updated template to CloudFormation, and CloudFormation is working out, well, what has changed, and then it'll make the relevant requests to, in this case, the EC2 instance, to make some changes to the security group associated with this EC2 instance. I'll just wait for that to complete. Tends to be fairly quick because there isn't a whole lot of changes that need to be done. Okay, so that's now completed. When I go back to the management console, and it essentially it has created a new security group rather than updated this one. So don't do a refresh on this security group. But if I go back to the EC2 instance, if I do a refresh here, select my, comes up. Select my EC2 instance, select my security tab. Here's the security group. Click on that. And in the inbound rules, you can now see that there is a new inbound rule added here. And specifically, it's the SSH and it's port 22. So port 22 is now open, which will allow me to send or make SSH connections. Now let's make an SSH connection. I need to know the IP address of my EC2 instance. So if I go back to instances, and if I select the general tab, where's my tab? Now here's the public IP address. There's also a private IP address. If I copy the public IP address, and command to make an SSH request from Mac anyway, I've just documented here for myself, it's going to be like this. The EC2 instance is running the Linux operating system, as I've said, and the Linux operating system will have an account for a user called EC2 user. So that's why I've got EC2 user here. The particular version of Linux that the Amazon platform uses, that's the way it boots the Linux server, creates an EC2 user. Now, if I just take this command, I'll explain the rest of the command in a moment, but if I take this command and run it from my terminal, so I'm okay with connecting. and eventually it will make the SSH connection. And now I'm at the command line within my Linux server running on the cloud, and I can do whatever I want to from there. Maybe install some software, start a server, etc., etc. Okay, so oh yeah, just to explain, the command there that I entered was this command. This part here, obviously, when we're using SSH, we want a secure connection to the remote server. And in order to do that, you need to have what's called a key pair. A key pair is a set of public and private set of keys to encrypt the communication between your desktop and the remote server. And you can create these key pairs using the management console. I wouldn't worry about it because you won't be doing any of this really in the labs, but I'm just demonstrating. If I just go back to the management console, you can see down here, there's a link for key pairs. You can see here, you go in there, you can just create a key pair. It's just literally, so I have a key pair created called EC2 CDK. And once you've created the key pair, you download what's called a PEM file. And I've downloaded that PEM file, and I'm referring to the PEM file. It's one level above, it's in the folder above where I'm currently located on the desktop. That's just to explain what's going on there. Okay, I'll close this connection. So that's our first look at this this cloud development kit. I should just also maybe show you the CloudFormation service itself. When we run CDK deploy for the first time on a new CDK app, then how you'll notice whether it has worked correctly or not is if you go to the CloudFormation service, you should see a new entry for your app, and that's this entry here is the one corresponding to the app that I have just deployed. Although strictly speaking, this is a stack, but because my app only had one stack, then there's only one new stack here. The other stacks were from some other work that I've been doing. So this here represents the stack associated with my demo app. You won't really need to do anything directly in the CloudFormation service, other than if you, well, if I now want to just destroy that stack, then the command is just CDK destroy from here, hit return, and it will take care of the rest. The CloudFormation service will take care of tearing down or removing all of the resources associated with that stack, which in my case would be the security group, the EC2 instance. There are some other resources as well, like an IAM role, which I haven't talked about, and one or two other resources, but it'll remove each of them, and it'll remove them in the correct order. Obviously, it has to, it would, for example, remove the security group before it would remove the EC2 instance, rather the other way around. On the very odd occasion when the CDK destroy doesn't work, what you can do is just go to the CloudFormation service directly and select the stack. Be careful that you do select the right one. Select it and then just select delete here. But you shouldn't really need to do that ever. Okay, back to we're going to be using the CDK right throughout this module. But you have hopefully just some sense of it. And in the lab connected with this set of slides, in the lab, if I just quickly go over to the website, There is something in order to use the CDK framework, you do have to what's called bootstrap your AWS account. And I'm explaining here at the beginning of this lab what the bootstrapping process is. And once you have bootstrapped your AWS account, then essentially what bootstrapping involves is creating a stack on your account in a particular region, and that stack is used by the CDK framework and CloudFormation for all subsequent deployments that you do of apps. And if I just go back to CloudFormation there, this stack here, okay, this stack called CDK Toolkit, this is used by the CDK framework and CloudFormation to facilitate the deployment of your other apps. So make sure never to delete this stack here, because if you delete that, then the CDK framework no longer works for you and you have to reboot your account all over again. But now in this lab, you are going to be deploying arguably a very sophisticated stack. It's going to comprise of two EC2 instances. It's going to have a security group with particular settings. It's going to have something called an auto scaling group. It's going to have a load balancer. Now, those of you that studied the cloud automated cloud services module in third year, you would be kind of familiar with the notion of an application load balancer and an auto scaling group. Essentially, an application load balancer, what it does is it takes requests and it balances, it distributes the requests to the set of EC2 instances. So our EC2 instances are going to be running a simple web server. But as we send requests to the web server, it's going to go via this application load balancer, and the application load balancer is going to distribute the requests evenly enough anyway between the various EC2 instances. Now, you don't really need to fully understand this infrastructure, because after this week's lab, we will not be using EC2 again. So we don't really need to delve into it. But the infrastructure is quite sophisticated. So for those of you that haven't done any AWS stuff before, don't be too concerned with fully understanding all the various parts of this particular infrastructure. As long as you just get the lab to work, then that's fine by me. Right. So I've introduced the CDK framework. The next thing I want to do is talk about this notion of serverless architectures. Maybe just before I do that, I want to do CDK destroy. And I let it work away in the background. And we'll just watch it for a second, but you can see here, look, it's deleting individual resources. It's kind of working its way through it. Now there aren't many resources as I indicated. Of course, the last resource it will delete is the actual CloudFormation stack itself. Anyway, we let it work away in the background. So I want to move on to serverless. And again, a set of slides. I won't complete the serverless topic today. And there is also a lab that you should be able to complete this week. So you've got two labs to work on for this week. You will not need to submit this lab either. So if I bring up my set of slides. So I'm just going to stop sharing my screen for one moment. Can somebody confirm that you can now see my slides again? Does anybody just want to confirm that you can see my slides?
Yes, we can.
Great. So, serverless, what's this all about? The first thing to say about serverless is it does not mean that there are no servers being used in our infrastructure. They certainly are. You always have to have servers. But what serverless means is that we as developers, we don't need to concern ourselves about provisioning servers and configuring them. And that's why I said there a moment ago that really after the first of this week's labs, um, we won't be using the EC2 instance because EC2 is an example of a server resource in the AWS world. But in this module, we're very much pursuing a serverless architecture for our applications. Hence, we don't need to use EC2. So we don't as developers, we don't need to care about the servers, and we don't have to manage the actual servers in terms of configuring them, provisioning them, um, making sure that whatever operating system we're using is fully up to date and patched, all that kind of stuff. So all of the concerns that I'm mentioning here on this slide, these are all things that as developers, we don't need to concern ourselves with. They are very important issues, but we don't need to concern ourselves with them because essentially uh, the AWS cloud provider is going to take care of dealing with these things behind the scenes for us. So we don't have to worry about what size servers do we need, how many servers do we need in order to deal with uh, capacity or scalability. We don't have to worry about making sure our servers are fully patched, or if our server crashes, we don't have to worry about rebooting it, getting it back up working again. The cloud service, the cloud provider will take care of all of that. So lots of issues that were a headache for developers pre the serverless era now no longer are a concern. And that means whatever time and energy was consumed in dealing with all of these issues, that time and energy now can be focused on developing actual application functionality. So no servers to provision. Probably said it too many times at this stage. Also, we don't need to worry about the scalability of our application. Scalability means if our if there are functionality that's running on the server side, if there's certainly a large volume of requests targeting our application, obviously we'd like our application's response time to be as quick as it would be if the volume of traffic was low. So the way you achieve that is by scaling up your server side functionality, adding more CPU power, essentially, I guess you would say, to it. But that's something that has to be managed. And previously, we would have to manage it, probably by having multiple EC2 instances running our application, and having a load balancer distributing the workload between those EC2 instances. So all of those concerns and are no longer an issue, but scalability still is very important in this serverless world. So bottom line is the AWS platform takes care of it. Also, when we did have to buy servers and do provisioning of them ourselves, that usually meant that there was quite a large upfront cost associated with them. But in the serverless world, you only pay for however much traffic is hitting your application. It's kind of pay for value approach, you would call it. Also, the availability of our functionality, in the server oriented world, if your server crashed and went down, then clearly it's not available for dealing with requests. And we were responsible for ensuring that the server was rebooted and our application was restarted within the server. But all of that now is no longer a concern in the serverless world. So lots of benefits to this serverless approach. Of course, it also means that you lose control as a developer. You lose control of the server. Essentially, you're handing control over to the, in our case, the AWS platform to take care of all of the issues that I'm mentioning here. I'm just going to kind of skip over that. Now, in the on the AWS platform, there are many services that would be categorized as serverless, and we are just going to look at a small number of them within the time frame available to us. The AWS Lambda service, for example, is an example of a serverless compute service. In other words, it's an alternative to EC2. EC2 is a server-oriented service. AWS Lambda is a serverless compute service. DynamoDB is a serverless database service, and in particular, it's a NoSQL database. I'm assuming people are familiar with NoSQL from other modules they've studied. AWS Cognito is a serverless service for managing user accounts. Hopefully we'll get to use that. API Gateway is a serverless service for creating HTTP REST endpoints, which we'll be familiar with from the module that you did in the first semester, the web app dev module, and so on and so forth. So lots of other services. We probably use S3, but we won't be using any of the other ones. We'll hopefully use SQS. Do I mention SQS there? Don't think I do actually. But certainly the first few we'll try and use. Now on the right, I'm showing you what we're going to try and achieve in the first assignment, I suppose you would say, for this module. In the first assignment, we will be developing a web API on a serverless platform. And so we're going to have a number of Lambda instances. That's where we'll implement our functionality. We'll have an API gateway, which is going to take care of receiving requests from our clients. Our client will just be Postman, but in general, it might be a React app or some other type of browser-based app, or it could be a mobile app as well. Requests to our set of Lambdas, but this gateway will take care of routing the request to the appropriate Lambda. The Lambda does its thing. More than likely, the Lambda will be talking to a database. In our case, we're going to use DynamoDB as our database, a serverless database. On the right here, I'm mentioning Cognito. So typically when the user wants to log in, they will use the Cognito service to take care of authenticating the user, checking their username and password combinations. And then once they're authenticated, they will be okay to send requests to whatever Lambda services that implement the functionality. On the left here, I'm mentioning S3. S3 was typically where we would deploy our front end, like our React application. We won't get to do that though in this module. So we're very much concerned with this part of the architecture. So, sorry, just to go back. So we need to kind of work our way through some of these serverless services. And the first one that I'm going to look at is the Lambda service, which is a compute service. So it's a serverless compute service. In other words, it's where you can deploy functionality, deploy your application code, and it takes care of running your application code. And so that means it needs to provision some CPU power, some RAM memory, some network bandwidth. All of that would be part of what the Lambda service manages for us. And what we deploy to the Lambda service is essentially just a function. We can deploy units that are of that scale, rather than in the server-oriented world. What we deployed was an entire application. So we would deploy an entire application onto an EC2 instance as one unit. But in the serverless world and in relation to the AWS Lambda service, we can deploy something as small as a function to a Lambda, to the Lambda service. And the Lambda service takes care of managing the utilities, as I said, that are required by that Lambda service. In other words, CPU, memory, network bandwidth. So I'm saying here it's custom code. So your function that you've implemented, it's custom code that runs on an ephemeral in an ephemeral container. Really, what happens behind the scenes is when you deploy a function to a Lambda service, whenever that function needs to be executed, and we'll see later on what might trigger the execution of your Lambda service, your Lambda function. We have the Lambda function and the Lambda service. The Lambda function is what we develop. The Lambda service is the service that takes care of running our Lambda function for us. But when you want your Lambda function to be executed, then what the Lambda service does is it essentially provisions a micro VM instance. It loads that instance with the relevant operating system, and then it loads your code into that micro VM instance, and it runs your code within the micro VM instance. When the code finishes executing, it essentially throws away or trashes the micro VM instance until another request arrives for the same function, and it goes through the same process all over again. If there are consecutive requests for your Lambda function, then it will probably use the same micro VM instance. It won't go through a full rebooting of a micro VM all over again. But this idea of an ephemeral container means that it just creates this micro VM instance and destroys it multiple times, essentially every time you want your function to be executed. Another way of describing this whole Lambda world is function as a service. So in this diagram, this is representing my Lambda function that I implement. This is implementing the Lambda service. On the left here, we're talking about the, sorry, if I just go back to the previous slide. Here I said that Lambda is an event-driven serverless compute platform. So it's events within the cloud that trigger the execution of my Lambda function. So I'm just using a simple box here to represent the source of the event. And the source of the event could be anything. Here I'm mentioning typically what the source or the trigger for your Lambda function is. It might be a HTTP request that arrives targeting your Lambda function. It could be a change happens to a database, and that change in the database is what actually triggers the execution of your Lambda function. We'll see how to do that, but it'll be a number of weeks down the line. It could even be a change to some other resource, a state change in some other resource. Like, let's say there's a state change to a particular S3 bucket that you have. A new object has been, or a new file has been uploaded to an S3 bucket. And that event is what you want to trigger the execution of your Lambda function. So the source of the event that triggers the execution of your Lambda function, you describe that in your infrastructure code. But whatever the source of the event is, when the event happens, that event is handled by the Lambda service, and the Lambda service then takes care of directing the detail of the event to your Lambda function. The Lambda function executes, and it can do anything you want it to do, include communicating with other services. Communicating with other services, do some processing, store something in a database, whatever. So the different parts of this diagram are the Lambda function, the event source, and yeah, okay. So there's the event source, which is the trigger. There is the Lambda function itself. The Lambda function can be implemented in any language that you want it to be implemented in. It doesn't have to be correspond to the language that you use for describing your infrastructure. In our case, it will be. We'll implement our Lambdas in TypeScript, and we're implementing our infrastructure as code in TypeScript, but they don't have to be the same. And equally, obviously, an application is going to be comprised of many Lambda functions. All of those Lambda functions do not have to be implemented in the same language, even though they're part of the same application. You may pick a language that's appropriate for a particular piece of functionality that the Lambda is performing. So just some general points here about the Lambda service. We're saying that it manages auto-scaling. So if I go back to the previous screen, if there's a high volume of these events occurring at any particular point in time, then what the Lambda service actually does is it creates multiple runtime copies of the Lambda function, and each one of them will handle one of the events. So that's what we call scaling up. So the Lambda service will take care of that automatically for you. If there's a low volume of events occurring, then maybe all we need is one Lambda function executing at any particular point in time. Each of these Lambda functions, so each of them is running inside its own micro VM. So again, as I said, if there's a high volume of occurrences, concurrent occurrences of this event, then the Lambda service will create a number of micro VMs, and the number it creates really, it scales up depending on the volume of the occurrence of the events. And each of these boxes now is representing a micro VM, and each one of them has its own copy of the actual Lambda function loaded inside it, as well as the particular operating system that's required by the Lambda function. And the Lambda service then will take care of directing the event occurrences to each of the, it'll direct them to, it will, sorry, load balance the events to the various copies of this micro VM instance. So that's how it deals with scalability. We'll talk a little more about scalability later on. So it does scalability, it does load balancing. The Lambda service takes care of any operating system management. So, you know, each micro VM will have its own operating system copy loaded into it. It makes sure that each micro VM is isolated from the other micro VM instances. So there's security isolation guaranteed, even though the micro VMs might be actually running on the same piece of hardware, server hardware. It will include that they're completely insulated from one another. It takes care of providing the necessary utilities that each micro VM requires in terms of RAM, CPU power, network bandwidth. So it does all of that for you. That's the benefit of this serverless approach. Over here, I'm talking about mainly the characteristics of what you develop. So you develop a function, and that's your unit of scalability. Whereas in the server-oriented world, you know, if there was a high volume of requests targeting a particular part of your application, you really had to actually make multiple copies, or multiple copies of the application had to be generated at runtime to deal with that high volume. Whereas here, we can scale up on the basis of individual functions within our application. I'm saying a function is a unit of deployment, as you'll see. It's very much stateless, so there's no sense that, you know, if I go back to the previous screen, if an event is sent to this particular micro VM and it deals with it, and shortly afterwards another similar event is sent to the same micro VM, the micro VM doesn't have any kind of memory of the earlier event that it processed. So in that sense, we say that the function is stateless. And you need to be aware of that when you're writing these Lambda functions. There is a limit as to how much runtime you can have for these Lambda functions. So I think the upper limit is 15 minutes. So if it's very heavy processing that's required, then maybe a Lambda function is not suitable. And they run on demand, that's okay. And so in terms of, from a cost point of view, you, as the customer, you're only paying for however number of occurrences of your Lambda function are being executed. So if your application is idle, then you're not incurring any costs because your Lambdas aren't being executed. So it's a kind of pay as you use model, or pay per execution model. So to dig in a little bit deeper into the Lambda function itself, just checking my watch here. Okay. So the Lambda function is a function. Okay, you can call it anything you want to, but conventionally we refer to it as a handler. So, and it's being invoked over the network, so it's being invoked kind of asynchronously. The Lambda function takes two arguments. We don't tend to use the second one that much. The first argument is the event argument or parameter, and that's going to contain the details of the event associated that triggered this Lambda function, if you like. And it can do whatever it's supposed to do. There's also some code here, which we refer to as initialization code. And what tends to be put here is if you need to make, for example, a database connection, if you want to create a database connection where the database connection would be used inside here, creating the connection, you would put that code in the initialization part of your Lambda file. You would not put it inside in the Lambda function itself. I'll explain why a little bit later on. And so the key parts of your Lambda implementation are the actual handler itself, which is the main part, I suppose. It's the function that is to be executed whenever the relevant event occurs. There's the event object parameter that contains the data associated with the event. There is a context parameter as well, which, as I said, we don't tend to use that much. But if you need to get some more information about the runtime context for your Lambda function, you could get it from this context object. And then there's the initialization code part of the Lambda function file, and that appears before the actual handler function itself. Okay. So you've written a Lambda function, and what kind of configuration? So that Lambda function is going to need a certain amount of CPU power. It's going to need a certain amount of RAM, and it's going to need some network bandwidth. And that's all part of the Lambda's configuration, which you need to describe in your infrastructure code. Now, what the AWS people decided was, rather than allowing the developer to specify each one of those three parts of the configuration, i.e. the CPU power, the RAM requirements, and the network bandwidth, what they decided is they would allow the developer to just specify the RAM requirements for the Lambda function. And based on the amount of RAM that was requested for a particular Lambda function, the AWS platform then would compute the CPU requirements and the network bandwidth requirements based off of that. So essentially, you only have one dial that you can control, which is the amount of RAM that is allocated to your Lambda function at runtime. And from that, then the AWS service itself determines how much CPU power should be allocated to the function at runtime and how much network bandwidth should be allocated to it at runtime. And I'm giving you just some details here. We won't really go into this kind of configuration in this module, but I'm just telling you that the minimum amount of RAM that you can allocate to a Lambda is 128 megs, up to a full 3 gigabytes of RAM in units of 64 megabytes, it seems. And as I said, the more RAM that you allocate, the more virtual CPU power is reserved for your Lambda function. So I'm just documenting this stuff here, but we won't really get into the computing these kind of configuration settings necessarily. Demo time. Okay, I have time for demo. So I'm going to do a different app this time. Just going to undo all of those first. So this is another CDK app. Same folder structure as before. Very little inside in this as before. Okay. Most of it is commented out. Actually, I probably should have removed it entirely. And this is where we have this is our actual Lambda implementation, our Lambda function. And this is where our infrastructure. So let's look at the infrastructure first. And so here's how we get AWS to provision a Lambda resource for us. And in our case, because we're writing our Lambdas in TypeScript, there's a nice convenience class called the node functions class, which I'm just implementing from where am I implementing it? Okay, well, I'm importing this particular part of the CDK, the AWS Lambda part of the CDK, because the CDK framework is quite large, as you might imagine. Covers all of the services, so you'd only really need to import the ones that are required by your particular infrastructure. And in this case, we're only implementing the Lambda one, the Lambda part of the CDK framework. And looks like we're creating an instance of something called a node function. A node function construct. This would be another example of an L2 construct. And here are just some configuration settings for my Lambda. Again, some of them I could have left out because I would accept defaults. So it seems I'm being specific about the particular hardware architecture that I want my Lambda to run on, even though it's not really important in this case. I'm specifying here, I am specifying that I want my Lambda that I want the micro VM, to have the node version 18 installed on it. So that's a particular requirement in terms of the micro VM. Here I'm just saying where my Lambda function implementation is, and that's just referring to this file here, which I'll look at in a second. And finally, I am specifying the timeout for this Lambda function. So I'm saying it should complete its execution within a 10-second period, which is probably well over provisioned actually. If it doesn't complete its execution within 10 seconds, then the Lambda service should interrupt the execution and treat it as a failure. Note I'm not specifying any RAM memory. I'm just accepting the default, and the default is 128, which is the smallest amount of RAM. So, and and there's one other part to my infrastructure, which is this part here. What I want to output when I run this piece of infrastructure, I want it to output to the terminal the full name that the Lambda service gives to my Lambda function, because I will use that name then to invoke it. So the name that I'm using here is this name here. It's only kind of part of the name that will be attached to this Lambda function by the Lambda service, as we'll see. So really this stack only comprises of one resource, a Lambda function. So let's deploy it. And as before, it goes through creating its CloudFormation template. I'm happy with that. And while it's doing its thing, if I switch over to the management console, and go to the Lambda service, so this is going to show me all of the Lambda functions that are deployed to my AWS account, and in particular in the Ireland region, or the EU West 1 region as it's called, which is what I've selected here. So if I just expand this here. So if I click on functions, Has it deployed? Yes. Why can't I see it? Let's see if I do a refresh. Okay, there's my Lambda function. And the name it has given it is, it's really the stack name plus the Lambda name plus a randomly generated hash string, essentially, just so that the Lambda's fully qualified name is unique, I guess, within this particular region. And also, I'm getting the Lambda name output here on the terminal. So this line in the output that was generated by this statement here in my infrastructure code. Now, how do I trigger the execution? Well, before triggering, if I look at the actual Lambda, very uninteresting, doesn't have any initialization code. Here's the handler, and all it does is a console log, and it returns a simple 200 response because it's going to be invoked over the network. It returns a 200 response and a message that reads like this. Yeah. Now, to trigger it, the only way I can trigger this particular Lambda is by using the CLI. And the command to do that is this command. So AWS Lambda, invoke whatever the name of the function is, and the response that comes back from the Lambda, you have to store that in a JSON file. You can call the JSON file anything you want to. I'm calling it response.json, and that file will appear now on my file system. In fact, you can see there's one here already because I ran it previously. But if I just delete that, and if I run my Lambda or trigger the execution of my Lambda, now the name of the function, I do have to replace that with the actual function name, which I can get from here. So this is just the response from the Lambda service itself, but the actual response from the Lambda function is going to be contained in my response.json file. And you can see it has recreated the response.json file here. And if I open that up, then it's actually the JSON that was specified in the return statement of the Lambda function itself, which was this here. This part here. Now, there is a console in terms of the console log statement that's in the Lambda function. The question is, where does that go to? Where is it outputted to? Or how can we see the output of that console log statement? On the AWS platform, all console log statements from Lambdas are handled by another service called the CloudWatch service. So if I quickly bring up the CloudWatch service, this CloudWatch service is used by many services within the AWS platform, not just Lambda. And if I click on log groups, now in the case of Lambdas, for each Lambda in your application, there is a log group created by CloudWatch for that Lambda. So if I select log groups here, you can see there's a log group, and the name given to the log groups is constructed by the CloudWatch service itself. And so it's made up of the name of the service that this log group relates to. In our case, it's AWS Lambda. You can see at the beginning there, followed by essentially the name of the Lambda function. But there are, as I said, other services use this CloudWatch service as well. So those other services, their log groups obviously would not begin with AWS Lambda. Anyway, if I click on this log group, a log group is comprised of what are called log streams, because our Lambda function might be triggered many, many times. And so there's a different stream created for essentially each execution of my Lambda function. Now my Lambda function has only executed once, so there's only one stream here. We can see that at the bottom. If I click on this is what a log stream looks like. And if we expand these, and in particular, if I expand this one here, and if you look across, here's what we can see what the actual console log statement wanted to output. So I was invoked. That corresponds to my console log statement. And using CloudWatch is something that you will be using quite a lot, mainly for debugging, because when you're debugging your Lambda functions, the way you will do it, it's quite primitive, but you'll put some console log statements in your Lambda functions, and then you'll trigger the execution of the Lambda, and then you look at CloudWatch log streams to see what each console log statement produced, and do your debugging from there. Okay, kind of out of time now, but in terms of the lab associated with this set of slides, this one here. So you will be able to do, let's see, certainly you'll be able to do the first part of it. And that's about as far as you'll be able to get. But you should just complete the first part. So the first part is this part here, standalone Lambda. The next part talks about Lambda URLs, which we didn't get a chance to look at. Okay, so you've got both the CDK lab and you've got this lab that you will need to work on this week. I'm going to leave it at that for now, and I'll talk to you on Friday, I guess, in the labs. So I am turning up for the labs in the lab rooms if you want to attend. Okay, bye-bye for now.